Nanti kan pembicaranya kan ngomong, nah itu enaknya direkam pakai apa ya? Maksudnya biar yang nggak datang bisa mendengarkan rekamannya. Hah?
Saya bisa cuma
Pakai apa? Biar orangnya suaranya masuk gitu ya.
Jadi Bapak, ya kameranya pakai pembicaranya. Oh,
jadi diajarkan sini nanti.
Ya, jadi beliaunya kalau bicara gitu.
Jadi ini orangnya bilang pacarnya itu mereka dunianya juga nanti dengan yang ibu kan ya jadi kita boleh yang tahu
itu masih naik.
jadi apa kamu udah dengar bisa dibuat bahwa itu satu orang yang sama gitu. Seingat saya kalau
Jadi kamu jadi bisa. Nah, ini kan problematik, tapi distribusinya itu kan ada yang itu akan
dalam streaming tentang ranking kuliner sama nek ngarani saya akan beri karena begini saya ikut sebenarnya apa punya dari sini orang bilang aku tidak itu betul ya itu saya itu sekali kalau aku udah masih bisa kan itu ya mengumpulkan kita intervensinya jadi
Okay, check. Can you hear my voice, please? Okay. Okay, Assalamualaikum warahmatullahi wabarakatuh. Like the previous weeks, today we will be holding the guest lecture with Prof. Ali Ahmadian. Okay, because this is the first time I have become a moderator for guest lecture Prof. Ali. Allow me to introduce myself. My name is Iksan, and I'm a student currently pursuing a bachelor's degree at Airlangga University. Okay, how are you today, Prof. Ali? Hello, Prof. Ali. Can you hear my voice clearly?
Dari sini sudah terdengar, Isan. Suara saya terdengar atau tidak?
Terdengar.
Prof. Ali, bawa. Assalamualaikum. Iya, ada respon juga. Sebentar saya coba kamu cek, Isan. Prof. Ali.
Oke, baik.
Assalamualaikum, hello. You can hear me because I cannot hear you.
Okay, I hear you, Prof.
Okay,
now
okay,
you
now,
can hear me.
yes.
Okay. Okay, because this is the first time I have become a moderator for this lecture. Prof. Ali, allow me to introduce myself. My name is Iksan, and I'm a student currently pursuing a bachelor's degree at Airlangga University. Okay, Prof. Ali, how are you today?
Fine, thanks. How are you?
Okay, very good, Prof. Especially next week's final exam, and after that, a semester break.
Oh, okay. So I hope all of you could pass your exam perfectly, receive good marks.
Okay, thank you, Prof. Okay, like the previous meeting, this time that Prof. Ali will present further material on fuzzy logic with 90 minutes, and at the end there will be a question and answer session if there are things that are still not understood by class participant. For class participant, you can submit the question via the column chat or immediately raise your hand. Okay, Prof. Ali, are you ready to deliver today's lecture
Yes.
material?
Thanks.
Okay.
Yeah, I'm ready. Let's
The
start.
floor is yours.
Okay, thanks. Let me share my screen. Okay, so Assalamualaikum and morning, everybody. Hope you pass a good week. And so, as your mate mentioned, that I think that you are in the semester break, and so midterm, I think that's semester break, not semester break, probably. So everybody could get good marks. What we have today, we will fuzzy derivatives, and fuzzy differentiability, and also fuzzy differential equations. Then we will go through so you can hear me. I think that
Okay, your voice is
just
clearly. Well,
yeah, it's okay. Okay. I thought that I have problem. There is problem with my sound. So anyway, so I just told you that today we have a review on fuzzy differentiability, fuzzy derivatives, and a part extension principle, Zade extension principle. And so one point from last session has been missed. At first, I think that I go through this important thing, then we will back to the extension principle and continue with the fuzzy derivative, fuzzy differentiability, and if we have time, a very brief approach to fuzzy fractional calculus, because I think that till today, if you search the literature and find the articles, I don't know how many of you are undergraduate or postgraduate students, or so if you are postgraduate students and or undergraduate and familiar with the research, and you check the articles related to the numerical methods on fuzzy fractional calculus, because fuzzy fractional calculus is a very hot topic, and so the results, if there are enough novel, so will be considered by high prestigious journals. So if you check the literature, you will find a lot of articles related to the numerical methods for fuzzy fractional differential equation. Fractional differential equation is the type of differential equation, but the difference is that in the ordinary differential equation, we have the derivative is of order 1, 2, 3, or anything. So integer order, I mean. While for fractional, we can so we can have other values like the values between 1 and 2, like 1.5 or 0.5, something the order of the. That's why we call it fractional, because we have some fractions. So anyway, if you search the literature and find the numerical articles related to the numerical methods for fuzzy fractional differential equation, almost 70% or even 80%, I want to be optimistic, I consider 70% or 80%, or otherwise maybe 90% or more. So because the other did not have knowledge perfectly, or they have not studied the fuzzy concept, just wrote some theorems, try to fuzzify them and write an article. So around 70% or 80% of these articles are completely wrong. That's why we can tell that if we are students or researcher, the knowledge beyond the fuzzy concept is important, then we can expand it to the other branch like fractional calculus and define or study the relative definitions and so on. So anyway, today we will go through the differentiability based on fuzzy concept, derivatives based on fuzzy concept, and also if we have time, hopefully we reach to the fuzzy fractional calculus, as I mentioned, a very brief approach. Just have a look on the definitions to see that what is the difference between the definition of the fractional derivative and fuzzy fractional derivative. Anyway, so let's go through the, if I can, in this. Okay, let me stop it and then back. Okay, so now if we want to go through the important theorem extension principle. So, but before discussing about extension principle, I go through an important thing that was missed the previous session. Okay, in the previous session, we talked about the different type of fuzzy number. We know that what is fuzzy set. We know that fuzzy numbers is a type of fuzzy set that is a convex and normalized. So that's why we call it fuzzy number. So, and then we have different type of fuzzy number, rectangular, triangular, and so Gaussian, bell shape. But the most common one or usable for us is the triangular fuzzy number. So and after that we talk about alpha cuts. We mentioned that if we have like if we have a set of fuzzy, so and when we want to get an alpha cut, then so will be all x belongs to universe such that the membership of this x over the fuzzy set A should be greater or equal alpha. This is the alpha cut. We already discussed about it. And then, so I already mentioned that this definition is very important, or this concept, the alpha cut, is very important. And I told you that by increasing the value of alpha, we know that alpha belongs to the closed interval 0 and 1. And if alpha 1 is greater or equal alpha 2, then the set, the alpha cut alpha 1 is a subset of A alpha 2. Okay. This is the important property of alpha cut. Or I told you that in the textbooks we have different notation for this cut, that we are trying. This cut is a crisp cut, means that we cut a part of a fuzzy set which is crisp, and then it makes easier for us to do some computations or anything that we want. So, and what else is that in some textbooks we have alpha cut, these notations, or sometimes they call it R cuts. This is the notation for to indicate the alpha cut or R cut, any cut of a fuzzy set. So then what else we have? Let me here. Okay, so I told you that the most common fuzzy number for us is triangular fuzzy number. The representation of the fuzzy number is like A1, A2, A3. If in a textbook or if in an article, you see that the fuzzy number, triangular fuzzy number with this notation means that it is actually a fuzzy number which is triangular. Then it has a membership function. The membership is defined like this one. For all x less than a1, it's 0, while for greater than a3 is also 0. Then for all values, for all x between a1 and a2, the membership is x minus a1 over a2 minus a1, while for all the values between a2 and a3, we consider a3 minus x over a3 minus a2. This is the membership function, okay? But important thing that we want to work with the triangular fuzzy number. So in computations, then we need to have an alpha cut of this fuzzy number. How we can, this is the representation of the triangular. So you can see that we considered 3 vertices or 3 points to show the triangular fuzzy number A1, A2, A3. Okay, so now we want to get alpha cut of this fuzzy number or show it by A alpha. For all alpha belongs to 0 and 1, it's the closed interval. So how we can get it, this alpha, or how we should write the A alpha equal, we usually get like A1 alpha, A3 alpha. We ignore, for alpha cut, we ignore A2, okay? But it will engage in our computations while we ignore it in representation of the alpha cut. So the alpha, it can be calculated in this formula. So you can see that A1 alpha minus A1 over A2 minus A1 equal alpha. So, or so make it easier for us, this is the general formula for getting the left and right side of our alpha cut. So this is one of the most important definitions related to the fuzzy set. If I want to get alpha cut for any alpha, arbitrary, so then A1 alpha is A, like what we should do is A2 minus A1 times alpha. So alpha can be anything. We write it as a general symbol, alpha plus A1. Come from here, okay? And A3 is equal A3 minus A3 minus A2 times alpha. We have a parenthesis here, should pay attention. If we do this formula, we follow this formula, then we get the number and or interval based on left and right, based on the numbers including alpha or depending on alpha, the left and right side as well. Okay, so let's see it in an example. We can write it in directly. A alpha is A1 alpha, A2 minus A1 times alpha plus A1 minus A3 minus A2 alpha plus A3. So you can see this formula. If we know this formula, then we can get any alpha cut for any triangular fuzzy number. So then I will show you that what is, so this is very important for us to deal with the fuzzy differential equations, because in fuzzy differential equation we have like differential equation, we have initial values. The initial value is usually a triangular fuzzy number, but once we want to work with it, we should consider alpha cut, even for function, even for numerical method that we will explain later. So anyway, this is the formula. So I have a question from you now. I stop here. I have a triangular fuzzy number, -5. You can see that -5, -1, and 1. So then you can see the fuzzy number. Give me the alpha cut of this fuzzy number. So you know the formula. I asked you this question. Let's start. I want to see that how you can get the alpha cut from this triangular fuzzy number. Give me an answer, please. You have the formula. Now I ask you to get an alpha cut of this fuzzy number considering the formula that I just explained. I'm waiting for you, anybody, to answer me in the chat box. This is our triangular fuzzy number. I want the alpha cut of this triangular fuzzy number. It's very easy, just a way to put it in the formula to get the alpha cut. Anybody could get the answer? Please share in the chat box. If we have this triangular fuzzy number and ask you to find the alpha cut of this triangular fuzzy number, because we need to do some computations. So what is the answer? Waiting for your answer. Anybody? No one could get the answer? Okay, so it's a very, very easy to get this alpha cut from the formula, we have a triangular fuzzy number. What is the formula for alpha cut? Is that if we have, in general, we have A1, A1, A2, A3. So then we put in this formula to get A alpha. So we do not care about the membership. We want to get the alpha cut. So this is the representation of the triangular fuzzy number here, -5. You can see that we show it with 3. So what we have, 3 components. We have -5. The vertices is -1 here, and last one is 1. Then we make a triangle. So anyway, we want to find the alpha cut. We can follow the formula. So you can use what we have here. We have -5. I just want to follow this formula because it's very, very simple. So what we have A alpha. I want to write it A1 alpha, A3 alpha, or -5 alpha, -1 and 1 alpha. So okay, no matter. We can write it like -5 alpha and the last one 1 alpha. What we have, the left one. Okay, so let me change the color to make it so clear. We have A2. This is A1, A2, A3. Okay, so we have A2 -1 minus A1 -5 plus 5 alpha plus A1. What is A1? Is a -5. So for right side, we write it minus A3. What is A3? 1. Minus A2. -1, so plus A3 is 1. We have here alpha. Okay, so this is the alpha cut we have. So we have actually 4 alpha -5, and what we have here -2 alpha plus 1. This is the alpha cut of the fuzzy number described here, that, and also 4 alpha -5 -2 alpha plus 1. So you can see that we write it. Then if anybody, this is the general formula for this fuzzy number. If anybody asks you to get, for example, like you can see that for alpha 0.5, means that you should replace alpha equals 0.5 here. 4 times 0.5 minus 5, it's equal -3, and -2 times 0.5 plus 1 will be 0. So this is the alpha cut for alpha equals 0.5. The important thing that I wanted to share with you, that considering the fuzzy number, that the maybe in differential equation, maybe in any type of computation that you want to work with it, if we have triangular fuzzy number, then you want to extract a alpha cut which is a crisp, and then you can work with the crisp set. So this is the general formula. Okay, it was missed from the past session. Now we're back to our main part as well. What we have here is the extension principle. I want to simplify the meaning of this extension principle, just give you a general image of what is the meaning of this extension principle. It says that if we have a fuzzy set, like I have a fuzzy set like A, I call it A, capital A, and a non-fuzzy function, and so I want to implement this non-fuzzy function over this fuzzy set to see the output. This general algorithm of implementing non-fuzzy function or running non-fuzzy function for a fuzzy set, and the output, considering the output should be fuzzy or should be non-fuzzy, the question actually. So this process is described under extension principle. Like I have a set of fuzzy set that the members are around 0.2. Okay, means that I have some members, each one, you know that I explained that each one has a specific membership function, and this fuzzy set is a set of the numbers or values about 0.2. Then I have a function like a x plus b. It's a function that I have, f of x. I want to put x, which are member of fuzzy set, talking about them, or members are about 0.2. I put here a times x, while x are fuzzy set, plus b. This process so give me a fuzzy set for output. This is defined under theorem of extension principle. This is just, I want to give you a general image of what is extension principle. So let's see based on the mathematical notations. I have a crisp function f from x to y. You can pay attention that I have, as explained, I have a crisp function, a non-fuzzy function. Okay, we have here f is a non-fuzzy function. A fuzzified function is what we have from f. This is the difference. So a type of transmission from x to y. Inverse is f inverse, f from y, fy to fx. We have fuzzified f. We'll explain how we can it. So extension principle is trying to fuzzify or crisp function. Okay, I have a crisp function and I have a fuzzy set. I want to consider the domain or the domain of our function is from fuzzy set. Then under extension principle, we want to make this crisp function as a fuzzy function. This is the way that we can fuzzify the crisp functions. So at first consider the crisp set. So what we have here, we have a crisp set. Like you can see that we have a crisp set, and then F transfer, you know that like calculus. So F over A will connect all of the members defined in the domain to some members defined in the range. Call it in here B. And the fuzzy state trying to say that we can define membership functions, fuzzy membership function for this range. Here is the membership functions of the set B. We are trying to fuzzify or set B. And then we also have here some memberships for A. Still, we are talking about crisp, okay? We are trying to fuzzify. Still, we are crisp. Memberships are in Boolean shape, Boolean value, same for A, same for B, okay? Then we want to connect the membership function, if we can connect the membership function of B to the membership function of A, then we can claim, if we can find a way to connect them, then we can claim that, or we can claim that we found a way to fuzzify or range. And then we can claim that we found a way to fuzzify or function. This is the way that extension principle is trying to do it. Trying to find some values in the range B and connect to the A. And if there is any way, then we can define the domain as a fuzzy set, while we know that the range is also fuzzy set. So the extension principle here is defined like this one. Mu B, or membership function of B, is equal mu, also mu function defined over FA, and effect on Y here, which are defined as a maximum of all mu's we can assign to the members here for A, or it's equal, while we know that X is equal F inverse Y, okay? We can define as a supremum of mu A. So it's maybe in your mind, it's confusing me for the first time, because we need to read again and again. We need to check the details. I completely understand you that at the first side, so you can see that what is happening. But I want to tell you that if we have a fuzzy set, so any number of fuzzy sets over the X in any number of universal that we have from X1 up to Xn, then we have actually, we can have, this is the extension principle, say that we can define or find membership function that connect the fuzzy states to the range of fuzzy set here under this function f. This is just a frame of extension principle. Extension principle is trying to make sure that if you have a fuzzy set and you have a crisp function at the first step, so you can find a range that this range is also fuzzy set, although f is non-fuzzy function. I give you a very simple example to help you to understand better, while some more details you can refer to the textbook, and if you're interested, because it's important principle or theorem, although we do not employ directly in our computations for differential equation, but we assume that the functions that we have in the differential equation, assume that they are defined under Zade extension principle. Okay, so like this one, this is a crisp function. And what we have A belongs to A for 1, 2, 3. Please pay attention that this is the notation for any fuzzy number. Sometimes in the textbooks, instead of 1, 2, 3, for fuzzy number, they use 1, 2, 3. Another fuzzy number, we have 2, 3, 5, or fuzzy set, no matter. X is equal 6. Then 6a plus b means that 6 times to a fuzzy set plus b is a fuzzy set. Output under a fuzzy, non-fuzzy function is also fuzzy set. To make it easier, we assume that it's a fuzzy number. Also, we can consider a general frame fuzzy set, no matter. But if we have a fuzzy number here, we write it like a x plus b. A and b are fuzzy number. Then we want to use extension principle. Extension principle say that you can employ any non-fuzzy value. You can have fuzzy value, and for x non-fuzzy value, you can have fuzzy domain and function is not fuzzy function. So all these things can, under extension principle, you can make a transformation, and the output is still fuzzy number or fuzzy set like C. This is a general frame of extension, Zade extension principle. Why we insist on Zade? Because we have other extension principles which are also discussed in the literature, but not very popular in differential equations. The most popular one is the extension, Zade extension principle. So we now reach to the fuzzy function and derivative. Just we discussed about fuzzy number, we discussed about alpha cut. We now aim to go through the fuzzy differentiability and fuzzy derivatives. Okay. From here, we had a look on the properties of fuzzy number in the very solid framework explained by the frontiers in fuzzy. Still, keep in your mind that fuzzy number is normal, convex, and so we usually, if it's triangular, we usually show it by 3 components. And also we have alpha cut. If it's equal A, then alpha cut, we show it by 2 members and has a specific formula. But if you want to start to write articles or reports or presentation, any scientific output, so we should refer to the rigor scientific concept. For fuzzy number is also same. So we know that fuzzy number is informally is a fuzzy set that is convex and normal. But if we want to explain it based on scientific frame, it has more properties. The first say that this is referred to the article published by these authors, Diamond and Cluden. If we have a fuzzy subset of real numbers, we show it by U. Use from R to a closed frame 0 and 1. We have a fuzzy set, a subset of real numbers. Then U is a fuzzy number if satisfy the following properties. First, U is a normal, means that, as we explained already, the maximum value, or we can say that some members or some members of this fuzzy set can have 1. The membership is equal 1. Also fuzzy, also it is the fuzzy convex, means that U for any T arbitrary belongs to this board or range, so UTX plus 1 minus TY is greater or equal minimum value of both membership UX and UY. And U is upper semi-continuous. This is maybe it's just a not very well-known definition in calculus. So, but it's actually we have, means that U is a upper semi-continuous, means that for all epsilons greater than 0, there is some delta, again greater than 0, such that UX0 less than epsilon, and the absolute value of X minus X0 is less than delta. So this is a frame, mathematical frame. So you provided to make sure that it's a fuzzy number. But the most important thing is that for fuzzy number should be normal and convex. And last one is that the support should be compact, bonded, and you know that the properties of compact, we usually show it in the articles by CL, and also we can have something like this. If you search all the fuzzy articles, they start with this in the basic definition parts. They start with this one. And try to mention that we, in this article, use fuzzy number. And all the fuzzy numbers, the space of fuzzy number, they show it by RF, maybe different notation, but usually if we are defined in the real numbers, we call it the fuzzy space of fuzzy number by an index provided here. It can be F, can be anything. It's not important. Just we show it the space of fuzzy number by this notation. We already have this is a fuzzy number. You can see that it's the like triangular fuzzy number, while the membership is a continuous function. You can see that for if I want to show it based on three, for example, three members, I show 0, 1, 2. And then we can get the alpha cut using the formula that you know. The membership is here for less than A is 0 and greater than 2 is equal 0. Or we have a trapezoidal number, again it's a fuzzy number, and so it has a representation, and usually we show it with the 4 component, 1, 1 and 5, 2.5. 4 component we have. And this is, you can see that provided here an example that it is, although it is a fuzzy set, you can see that some of the members could achieve the value 1, but it's not a fuzzy number because it is not a convex. So from the figure, you can find it for any members. So if you select, then the tx plus 1 minus ty, so something like this for the convex should be greater of minimum of 2 members, while we can see from the figure it doesn't happen. Then we can tell that it's not a fuzzy number. So for fuzzy number should be convex and normalized, not only one of them. We also have singleton fuzzy number. This you can see that the singleton fuzzy number is usually show it. It's interesting because maybe in some textbook you can see this notation. So this is the notation for a singleton fuzzy number. Define that if we have R as a real numbers, then what we have for singleton is the fuzzy number that defined for over the real numbers and assign only one specific value. And what we have is pass it here. Okay. Here, as I told you, that we have alpha cuts, literature, and also R cuts. Same meaning, just different notation. Here you can see that alpha or R level set is for all x that ux greater than or equal R, while for you can see that support is support of a fuzzy state means that all the members, or we show it with U naught, all the values of members and membership function should be greater than 0. So this is the definition also of the support of a fuzzy set, or equivalent we can consider as a 0 level set or zero cuts. zero cut is actually support of a fuzzy set, or show its support of a fuzzy set is zero cut. Then we have stacking theorem. This theorem try to give you the properties of the alpha cuts that you want to use. So it's a very famous theorem proposed by Negueta and Rolescu. So very famous, prominent researcher in fuzzy. They provided this theorem to make sure that there is not any problem with the R cuts or alpha cuts. Here they use R cuts, no difference. So mention that if U is a member of space of fuzzy number, okay, means that U is a fuzzy number, and then UR is a R cut, then this R cut has some properties. You know that sometimes in the literature we have U, I told you U alpha, we show it by U if we have fuzzy number U1, U2, U3, U is equal this one, then we show U alpha, U1 alpha, U3 alpha, okay? Sometimes in the literature, we show it by UR. Then what we have, UR minus UR plus, means that the left side of alpha cut and right side plus for the right side. So they don't use U1 and U3. Instead, they use minus and plus. Minus and plus is only trying to give you the left and right side of the alpha cut that we have. So stacking theorem, they tell you that if we have a fuzzy number and you are the R cut, so it's actually UR is a closed interval for any R. And what we have, another thing that we already explained, if R1 is less than equal R2, that so they are in the interval between 0 and 1, then UR2 is a subset of UR1. It's very, very clear from the figure. If we have, for example, a triangular fuzzy number, and this is the, for example, U. So I cut with the alpha equal 0.2, okay? So this is assume that the cut is for 0 equal, alpha equal 0.2. Then if I consider alpha equal 0.5 and make it a cut, you can see that here, then the set and here set extract from this alpha. It is very clear that this set is a subset of this set. That's why I mentioned that if R1 is less than R2, then UR2 is a subset of UR1. And also for any sequence, we have a sequence of Rn, then the intersection of all URn, please pay attention, for n from 1 to infinity is equal UR. Okay, so we have an intersection, we have a sequence of Rn, R1, 2, 3 up to N and empty, then all these intersection is equal UR, while the support of the union of these set, this sequence is equal U naught. This is two important properties. But mostly we do not mention them in the articles and considering the first two. The first is the closed interval UR, left and right minus plus. The second one is that this UR2 is the subset UR1, while R1 is less than or equal R2. We have some characterization theorems. Till 2008, we only had this characterization theorem. This characterization theorem is trying to tell you some significant thing, properties of the subset of like MR. MR is a subset of R cuts. Okay, mention that this subset is non-empty closed interval for any R. Means that if we have an R cut of a fuzzy number, then it's non-empty, and we know that it's MR2 is the subset MR1. This is negotiator rural skew, and then the intersection of MR1 is equal MR. Explain it, and this union is equal M naught. M naught is the support of the set. So, if all these properties satisfy, then there exists a unique unique fuzzy number that UR is equal MR. MR is a family of subset that R belongs to 0 and 1. Don't confuse your mind, okay? Just a characterization theorem explaining some properties over the fuzzy numbers and R cuts, okay? We don't want to go through this detail, what the meaning, why we need it. But important thing that keep in your mind, if you can see that in the articles or textbook that this fuzzy number so satisfy stacking theorem, or you consider the negotiatorial skew characterization theorem, is that your fuzzy numbers satisfy in this condition. Up to 2008, we only had this characterization theorem. Why in 2008? Because there was a problem in the numerical article on solving fuzzy differential equation. Then Bede, a very important and efficient researcher, Bede, wrote a new characterization theorem over the developing numerical methods for fuzzy differential equation, which is very significant for solving fuzzy differential equation. But before up to 2008, sorry for my handwriting, up to 2008, the most significant one is this one. After that, we had the characterization theorem. And also, for the fuzzy numbers, we have another presentation or representations. We call it LU representation, proposed by Gauss-Schell-Waxman. They mentioned in this theorem that if we have u as a fuzzy number, and then we have r cuts, u r minus, u r plus. How we should find the r cuts? We know the formula. Then the functions u minus and u plus, so which are endpoints of our r cuts, should satisfy these conditions. First, u minus r, which is we call it u minus r. This is to make it shorter, is bonded the left side, bonded, non-decreasing, and left continuous function. Left continuous function. And it is right continuous only at 0. But for u plus, we write it u plus r. U plus r is a bonded, non-decreasing, left continuous, and it is actually right continuous at 0. And u minus, this is important, u minus 1 alpha cut at alpha equal 1 is less than or equal u plus 1. This is called LU representation. And then again, these researchers give a new revision for their over the previous property. They mentioned that u minus r will show it is bonded, non-decreasing, left continuous, right continuous at 0, and u plus r non-increasing. You can see that non-increasing, left continuous, and its right continuous at 0, u minus 1 is less than equal u plus 1. They mentioned that this is the representation of our alpha cut. We know that if we write u minus r, u plus r for our u r, then we know that it is both are bonded, the left is non-decreasing, the right is non-increasing, and this one left continuous, both left continuous and continuous at the right point, right continuous at 0, x equals 0 or u equals 0. Just we want, the most important thing is that we now are all of our reward that u minus r and u plus r are bonded and non-decreasing, non-increasing. Fuzzy functions and operations. We have some definitions about fuzzy functions that have been revised and corrected or improved over the years. This is one of the theorems proposed in the decade 80, I think. It mentioned that if we assume a continuous function, fuzz is not fuzzy function, a continuous non-fuzzy function, and we want to define it or fuzzify it, they assume that they have run extension principle, then we have a new function which is called fuzzy over a domain fuzzy and range fuzzy. W is defined over F, U, and V. W, we want to get R cuts. the R cut of this output, new output, which is fuzzy because F or new F is fuzzy. In fact, so the left side is the infimum fxy for x belongs to UR and Y belongs to VR. U and V are fuzzy numbers. And W plus R is the supremum of all if such that X belongs again to UR and Y belongs to VR. This is the first definition proposed for fuzzy functions. The left point of our output coming from our fuzzy function is the left is infimum and right is supreme. Then the question is here, if we have two fuzzy numbers, we want to work with their R cuts. How we can do for summation, for multiplication, for subtraction. The definition tells us, based on extension principle, if we have two fuzzy numbers, we want to make a summation and get the R cut. So it is in fact X plus Y, such that X belongs to this fuzzy number, Y belongs to this fuzzy number V, and the output is UR plus VR. Means that U plus V over the R cut is equal UR plus VR. I tell you that how we can do it. So, and for the multiplication of for any number, any lambda belongs to R, so times U, multiply by U, and then we want to get R cut. So output is lambda UR. Summation of two interval. Multiplication of lambda into an interval. There is not a difference. Let's see that in an example. If we have two triangular fuzzy number like U and V, then U plus V in fact is the first complement will be added to the second one. Second to the first one of V. Second one will be added to the second one. Third one to the third one. So we have 3, 5, 8. Why? Because we have 1 plus 2, 2 plus 3, 3 plus 5. Then we have this. And if we have any real number multiplied by a fuzzy number U, like U is equal 1, 2, 3, multiplied by 2, we have 2, 4, 6. Or minus 2 times V. Because we have minus, then should revert it. So will be minus, you know that minus 10, minus 6, minus 4. You can see that it's reversed because minus is multiplied. It's like quiz. There is not any difference. We have a theorem here that explains that U plus V, if we have two fuzzy numbers, is equal V plus U. Once we step in forward and understand the concept, then we can see that. And so not very confused with the details, you can see that the fuzzy calculus is not very difficult, while the main concept can embed in your mind. So the singleton set, like we show it with 0 plus any fuzzy number is actually equal for U, if it's U is a fuzzy number. So we have some properties related to the fuzzy numbers. If we have two fuzzy numbers, u and v, then multiplying by lambda as a real number, so we can multiply separately and then make a summation while we have. So also here the multiplication like lambda times mu times u for any we have here two real number multiplied by u. So it's no matter that at first multiply mu, then multiply lambda. So this is some properties of fuzzy number. While we have the product of two fuzzy number, usually we show the product of two fuzzy numbers by this dot. Okay? If we want to get the product of two fuzzy number, we should call it this product W is a U dot V. This is defined by a Zade extension principle. If you check the article, explain that how we reach to this formula. Anyway, using this stacking theorem, using Zade extension principle that I don't want to go through the details. We know that from the previous theorem, the left side is the infimum wide for the right side of alpha or r cut of a fuzzy number. We need to consider the supremum, the infimum of the multiplication of xy for any x belongs to u, y belongs to y, belongs to v. For supremum, same. But so if I want to get the product, means that what can I do? I should multiply u by v, the minus the left side, left by right side, right by left side uv, and both right side. Then select the minimum from this one and the maximum as well. So I have the product of these two fuzzy number. Let's see in an example what we have. We have a rectangular fuzzy number and triangular. Then u dot v. U dot v is actually 2r dot r plus 2. It's coming from the fact that you should first get the r cut, then you can get the left and right side. Means that you need to multiply considering this formula so you can find the right and left of this example. I ask you, please solve this one in your home, that how we should reach from these two fuzzy numbers, which one of them is triangular and one of them is rectangular, then multiplication we have here. This is the representation of the two fuzzy numbers. But we have that dot product. And also we have another product which is more popular and currently more applicable in the articles, anything that you can see in textbooks, proposed by Bede, and Bede, one of the prominent researcher I already explained, propose a new characterization theory. We will explain about characterization theory. So anyway, if I have u and v are the positive fuzzy numbers, okay, I have two fuzzy numbers. I want to get the multiplication of these two fuzzy numbers. I use this symbol. This symbol anywhere in the fuzzy articles, if you can see, means that refer to the multiplication of two fuzzy numbers. I want to get the alpha cut or r cut. So for the left side, say that you should consider u r v1. V1 is for alpha equal 1 or r equal 1. U1 VR minus U1 V1, and similarly for the right side. Then we write it. The left and right. This is the formula to get U dot V. Another multiplication. We have several definitions. I here presented some more popular ones for the fuzzy. So interesting thing here is that if we have a product of two fuzzy numbers satisfying this proposition, then the next proposition referring to this one tell us that if we have two fuzzy number and U is positive while V is negative fuzzy number, then U dot V is equal minus U dot minus V. This output is a negative fuzzy number. If U is a negative fuzzy number, I leave it for you to search what is a negative fuzzy number. I ask you next session, what is a negative fuzzy number? Please search it, it's very easy. If U is a negative fuzzy number and V is a positive one, then U dot V is a minus U dot V and is a negative fuzzy number. If both are negative, then U dot V is equal minus U dot minus V and output is a positive fuzzy number. This is important or interesting proposition standing for this definition, considering this definition. Or if you Google, so I asked you to search that, what is the meaning of positive fuzzy number? What is the meaning of negative fuzzy number? Please Google and give me your answer next week. I will ask you. And also I told you we have different definitions for product of a fuzzy number. It is the cross product of fuzzy numbers. If they have two positive triangular fuzzy number, then again, maybe in the textbook or article say that consider the cross product. The cross product tell you that if we have U is A1, B1, C1, V is A2, B2, C2, then cross product is A1 times A2. Sorry, A1 times B2 plus A2 B1 minus all the multiplication of B1, B2, B1, B2, B1, C2. So here we have one term, here we have one term, and here we have one term. Again, because we have triangular fuzzy number, we have three terms in output. The first term, the middle one is easy, it's B1, B2. The left one tell you that we have A1 times B2 and A2 times B1 minus B1, B2, okay? But for the right side, we have again C1, B2, consider these two. At first we consider the multiplication of these two components, then we consider the multiplication of these two components. B1 C2 plus B2 C1 minus B1 C1. This is the cross product. Example here we have, if U is equal to 3, 4, V equal 3, 4, 6, you can see that at first. So the middle one is a 3 times 4 is equal to 12. Then for this one, we should write A1. A1 is 2 times what we have here, B2. B2 is 2 times 4 plus A2 B1, A2 is 3, B1. What we have here, B1 is a 3 minus B1, B2 minus 12. If we make it, so then we can see the output is 5, while so we have also, we can consider the rest for this one. But general is the cross product. If you want to get it, this is the formula. So the difference of fuzzy number. We already had the cross product or multiplication of the two fuzzy numbers, different definitions we consider, then we reach to the difference of fuzzy numbers. Why we have the difference of fuzzy number with this notation? Because once Zade proposed a standard difference based on Zade extension principle, on that part, the property of the standard difference proposed by under extension principle, we reach to the fact that u minus u is not equal 0 on that part. If we have two fuzzy set or fuzzy number, and then we want to get a standard difference based on Zade extension principle, then we could reach the fact that it's not equal 0, and this is the shortcoming of the extension principle or results based on Zade extension principle. Because it's important to have u minus u based on a standard difference should be equal 0, while for the Zade is not. That's why several new differences proposed for fuzzy. And we still have from this one proposed in 1987, this definition, which is very, very popular. But after that, we had new one in 2005. Then we had again in 2009, and some revision of 2009 in 2000. I think that 30. Yes, this is the trend. So, but this one, the first one, and one of the most common one, while the next one is the somehow are the revision of this definition, Fukuhara. The Fukuhara difference, we show it by this notation. Fukuhara difference tell us u minus v, standing Fukuhara difference, equal w if and only if u is equal v plus w. This definition is trying to give some condition to avoid of u minus u is not equal 0 to solve this problem. While the plus here is the standard fuzzy addition, which is we normally add some fuzzy numbers like we have 2, 3, 4, and another fuzzy number is 2, 3, 4, 5. If we want to add, so the addition is equal, you know that 2 plus 3 is 5, 7, 9. So this is once mentioned that it's a standard fuzzy addition, means refer to the Fukuhara difference. Say that if you want to make a difference of two fuzzy numbers using Fukuhara, so it is satisfied if and only if u is equal v plus w. It is very good. Although it has some shortcoming that has been revise in the next revisions, but it's the basic or foundation of the difference of fuzzy numbers, which we use also in the fuzzy differential equation. Okay, so I stop here and we'll explain the rest the next session. And yeah, now it's open for any question or any comment from the audience. Thanks.
Okay, thank you so much, Prof. Ali. Anybody, can you question if you needs us to form Prof. Ali, just read, just write question in column chat or immediately raise your hand. Okay. Did anyone ask? All clearly, audience? Okay. Is there any addition from Prof. Ali?
No, not for current session.
Okay.
I just ask all of students which are motivated, maybe which they want to work on master thesis, or they want to pursue with the fuzzy concept, that to pay attention to the fact that you need to read the textbooks which we have for fuzzy starting, and then you can expand it to the differential equation. And definitely, if you have enough knowledge of fuzzy and fuzzy differential equation, then your output will be significant and you can publish your outputs in the high prestigious journals.
Oh, okay. Okay, because no anyone asking. Okay. Okay.
Oh, sorry,
One
just
question.
have a question. Yes, yes. There is not any difference. There is definitely just say a different notation. Some textbooks or articles use R cuts. Some textbooks is alpha cut. Just different alphabets of or different notation for using the showing the level set or cuts. There is definitely not any difference.
Okay, thank you, Prof. Ali, for answering. Okay, the last one. Did anyone ask? Okay. Cause no anybody asking. Okay, thank you, Prof. Ali.
Thanks. Thank you
for
so much for
being-
your attention. So I wish you a very nice weekend, and so all the best for all of you. And Assalamualaikum. Bye.
Okay, thank you, Prof. Ali, for being material about fuzzy logic today. I hope the material presented at today's lecture is useful for all of us, and see you next week, Prof.
See you. Bye.
Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.